Let's investigate the escape velocity of the Earth, define what it is, and calculate its exact value. A force is the quantity needed to change the velocity of an object, so to move it around. To continuously exert a force on an object over a distance requires spending energy, which we will call work. The expression for work is simply the force multiplied by the distance over which the object is moved. An example is lifting an object from the ground. Doing this, we need to continuously overcome the force of gravity that is trying to pull this object back down again, and thus we exert a force over the entire trajectory of this object. The total energy that is needed to bring an object from the ground to a specific height can be calculated. However, we cannot simply use the formula for work here because the force changes at every point on our trajectory. It is not constant. The higher we go, the weaker the force of gravity gets. Instead, what we want to do is to take this multiplication of the force, but now with an infinitesimal height difference, over which gravity does not change. And then we sum all of these pieces together. Now this sum over infinitesimal distances becomes an integral in the continuum limit. Therefore, the required energy, or the work, is reduced to calculating this integral. But what about the boundaries? Well, at the surface of the Earth, the force of gravity is given by capital G times m times capital M divided by r. And this will be the force of gravity at our starting point, so corresponding to the lower bound of our integral. And then we lift the object up to a height h, which will be our upper boundary. The distance from the center of gravity to the object we will call x. Computing this integral, we find the expression for the energy, or the work, that is needed to lift an object from ground level to a specific height h. And thus, now we know the energy required to lift an object up to a certain height. Escaping the gravitational field entirely, however, which is what we are after here, is achieved by lifting an object infinitely far away. Now note that theoretically you can never escape the Earth's influence, because gravity diminishes by 1 over r, which never really becomes zero. Thus, in our previous integral, we let h go to plus infinity and see how much energy this actually takes. Now you might expect that lifting an object infinitely high takes an infinite amount of energy, but computing this integral, we find a finite expression. And thus, to escape the Earth's pull, we need to expend this amount of energy as work. And this brings us to the escape velocity. We could expend this energy over the entire journey, such as, for example, a rocket that burns its fuel during the first hours of its ascent. However, what if we send our object into space by kicking it only once, very hard, at takeoff? Normally, when you throw an object into the air, it slows down and then comes back down again. But what if we gave it such an initial velocity upward that it escapes into space and never falls back down again? This is the escape velocity, and to be sure, its velocity will still decrease as soon as it leaves the ground, but just not fast enough to bring it back down again. So how fast is this escape velocity exactly? Well, let's find out. Sending something flying into space with the escape velocity basically means that all of the energy required to overcome gravity is given to the object with one violent push, giving it kinetic energy. Therefore, to find the escape velocity, we can equate the kinetic energy of the object with the total energy required to leave the Earth. Rewriting this equation to single out v, we find that the escape velocity is equal to the square root of 2 times g times m divided by r. And note that all of these properties are unrelated to the object itself. So the escape velocity is a property of the Earth itself, and it will be the same for any object that you can think of. To finish off, we fill in the numbers and conclude that the escape velocity for the Earth is roughly 11 kilometers per second, which is roughly 40,000 kilometers per hour or 25 miles per hour.